This is Shakil Ahmed. In this tutorial, we will discuss about Poisson regression. Poisson regression is used when we have count response variable. We want to check the association between a count variable and some other covariates on continuous or binary or discrete. So usually when we have events, number of events or number of births or number of certain disabilities in an area, then we need to model those kind of data using the count regression model. Count regression model is basically a generalized linear model with Poisson link, where we assume that the a number of events follows a Poisson distribution. So there are certain assumptions of Poisson process you need to check. The event should be rare and the probability of occurrence of an event in a shorter time interval is negligible, and the event occurrence in different intervals should be independent. So we have basically in Poisson process we have a given time interval and we see the number of occurrence of events in that interval. And if we are interested in the time uh, to occur a certain event, then we will use the gamma regression. That is another topic. So we start with the same stroke data. I check whether we have the data set or not. We need to check the data, and now I have uploaded the data, strokes data, and we can run the data. And in this data set, we can't see a count variable. Most of the variables are binary, are continuous, or multinomial. So we can, I just created a new count variable uh, between 1 to 10. You can start with 0 to 10, uh, including zeros as well. And the length of data frame is length is the same with this data. Basically, I am just attaching with the data frame as a new column that is called count. And you can see now I have added a column mentioning as count y. So we can use this variable as the response variable now in our regression model. We can first check the frequency distribution of the count variable using the matplot library and seaborn library, and then we can set the figure size and then the data we are using, and the x-axis we have count y, and this is the title of the plot, and this is the x label, and this is the y label. You can change on the x-axis we have values, basically 1 2 3, and on the y-axis we have frequencies. You can just make a bar plot or a line plot. So we can see this distribution almost follow a uniform distribution, as the data was generated from a uniform distribution, but mostly in real life situations we have a skewed, positively skewed distribution for the count outcomes. For example, number of events, number of uh, different occurrence, we can just model using it, just like a positively skewed a bar diagram. And then we can see, I have already discussed the assumptions of the Poisson distribution. The independent variable must be count or non-negative integer, and event must be independent, It's not independent variable, it's the dependent variable must be count or non-negative integer. Dependent variable. The average rate of events per unit of time or space is constant, and the probability of occurrence of event in a small interval should be negligible. And we can just extract the axis as age, hypertension, and heart disease. We just see the effect of these variable on, for example, number of uh, occurrences, for example, number of uh, conditions on different patients. For example, we have one patient have one condition, one patient has three conditions, one patient has four conditions. So we can just consider the count variable as the number of conditions. And then we will run a Poisson regression model. We need to import the states model as SM, and then the data y variable and the x variable, and then we can fit a Poisson regression model using y and x, and then Poisson fit, and then you can see the results. We can just print the summary of the Poisson results. So here is the summary of the Poisson results, including the number of observations. We have this much observations, and the degree of freedom for model is 3, and the Zoto R square is very low, and we can see the likelihood values. This is null likelihood, and this is the residual likelihood, and then log likelihood, and this is the p-value of the likelihood ratio, which is significant. So the overall model is, you can say, significant, and these are the coefficients basically. So these values tells the average number of occurrence of event, average basically change in the mean and number of events with 1 unit change in age. There is a small change in the counts with change in age, as these variables are not related to the counts, as we have generated counts randomly. So the coefficients are very small, but we can say with 1 unit change in I think we can say that, with no hypertension to hypertension, there will be a decrease in the count with 0.04. You can say the mean count will be decreased by 0.04, approximately 0.05, you can say. So and the for heart disease, it will increase by, the mean will be increased by 0.0137. So this is the interpretation of the coefficient, and these are the standard errors, and these are the z value. We are assuming a normal distribution as the sample size is enough, and these are the p values, and these are the 95% confidence interval. You can also show the exponentiated coefficients to these are basically change in log mean. If you want to see the change in mean, you can exponentiate these coefficients and present the exponentiated coefficient. And we can see the we can check the assumption of the uh, most of the important assumption in Poisson distribution is that the mean and variance are equal. So we can check this using computing the mean and variance. We can also do this by comparing the residual deviance, mean of residual deviance with degree of freedom. Basically, the degree of freedom is the mean, and the residual degree mean residual is considered as variance, and their ratio is regarded as, if the ratio is 1, close to 1, then we can say that uh, there is no over dispersion in the model. If the variance is greater than the mean, then there is a problem of over dispersion. Then we need to go for negative binomial regression and other options. So thank you for uh, concentrating on the video, and I hope you got something about applying Poisson distribution in Python in this video. Thank you.